finite element analysis of tensile property for the single strap butt joint of a carbon fiber reinforced composite. The abstract. To analyze the tensile property for the single strap butt joint of a carbon fiber reinforced composite, a finite element model was established using number 22 and number 185 material based on LS/DYNA with the tested data and the theoretical solution reported previously. Then the tensile property influenced by three factors were analyzed, that is the connection strength, the failure mode of composite, and adhesive stress. The result shows that the adhesive interface of zero stacking can greatly improve the tensile strength and reduce the composite matrix tensile damage. This is the diagram for structure dimension. uh, Model and material theory. The FE model was established according to the structural dimension material parameters introduced by lithium ET aluminum 11. The total length of the model is 210 mm and the overlap length is 101.6 mm. A total of two stacking sequences are set to each composite adherent that which are represented by S1 and S2 respectively. Considering the local effect, the global effect, and the accuracy of simulation result, the thick shell element is adopted to simulate the CRP adherent, which is divided into four plies in the thickness direction. Each ply is given four angles and four integrating points to define the integral calculation point and store the calculated result data of each layer. The number 22 material in LS/DYNA is selected for the composite plate, which is convenient to analysis the fiber matrix damage in the stretching process, while the number 185 material is chosen for adhesive layer element, which is only suitable for the solid element and can simulate the dynamic process of adhesive layer fracture. Theory of composite model. The number 22 material of composite laminates in LS die use the Chang composite. This is the diagram represents the sigma max. This is the reversible loaded when unloading. Failure theory and the stress strain relationship is determined by the following three equations. Epsilon 1 is equal to 1 by E1 into sigma 1 U1 sigma 2. Epsilon 2 is equal to 1 by Young's modulus 2 sigma 2 minus U2 sigma 1. 2 epsilon 12 is equal to 1 by G12 tau 12 plus alpha tau cube 12, where the E1 and E2 are the Young's modulus of composite for x and direction. E1 and E2 and E12 are the strain in the plane. S1, S2 and tau 12 are the stresses in the plane, while G12 is the shear modulus in the plane. In this equation 3 determines the nonlinear shear stress coefficient. Meanwhile, the shear failure mode of fiber and matrix is defined that that is the ratio of shear stress to shear strength as follows. Tau is equal to tau square 12 by 2g12 plus 3/4 alpha tau to the power of 4 suffix 12 by s square 12 by 2g12 plus 3/4 alpha s prefix 4 suffix 12, where s12 is the shear strength. The fracture failure criterion of the matrix can be described as follows. F matrix is equal to sigma 2 by s2 whole square plus tau, and the travels tensile strength. If a failure occurs, F matrix is greater than 1 and the material parameter E12, G12, Y1 and Y2 are said to be 0, and the compression failure criterion of the matrix is defined as F composite is equal to sigma 2 by S12 whole square plus C2 by 2 S12 whole square minus 1 into sigma 2 by C2 plus tau. where C2 traverse compressive strength and the failure is assumed whenever composite if composite is greater than 1 and the material parameters are said to be 0. The final failure mode is defined as fiber. So the equation is F fiber is equal to sigma 1 by S1 whole square plus tau. S1, the longitudinal tensile strength failures occur, F fiber is greater than 1 and the material parameters are said to be 0. Theory and adhesive model. The adhesive element is simulated by the material. So the number 85, 185 whose failure theory is defined by Hallquist et aluminum 16 and 17. It is the cohesive model only for the solid element. In this material, a dimensionless separation parameter is defined to describe the interaction relationship between the relative displacement in the normal and tangential direction as follows: root over delta 1 TLS whole square plus delta 2 TLS whole square plus delta 3 NLS whole square, where NLS is the maximum separation in normal direction, TLS is the maximum separation in tangential direction, and D1 D2 are the tangential relative displacement of model uh, 2 loading mode, and D3 is the normal relative displacement of the model 1 loading mode. NLS and TLS are the key values represent the maximum normal and tangential separation of contact surface. The material in tensile state when D3 is less than 0, when in a compression state when D3 is greater than 0, a trilinear consecutive relation can be described, and the consecutive relation is represented in a formula. The formula where A1, A2, A failure are defined by users according to material actual properties. Tensile stress displacement curve. The both curves is represent the tensile and displacement. The tensile stress is represented by megapascals and displacement units are mm. In this first curve, the curve starts at 0 points and raises the tensile stress between 200 and 300, and in displacement it between 1 point near to the 1 point the displacement curve occurs. Analysis of mechanical strength. When inputting the material parameters, composite laminates are provided by lithium aluminum 11. However, the constitutive relation of adhesive material is not described as the stress strain relation. Therefore, the parameters such as NLS and TRS are adjusted when carrying out FE simulations, and then the calculation results are compared. When the stress and tensile stress displacement curve obtained from the test and theoretical solution, hence FA model which is conforming to the test result and the mechanical solution can be obtained. The diagram represents the mechanical strength of adhesive layer crack. Effect of stacking sequence. According to the first movement, adhesive cracked the tensile stress displacement curve, and curve of S1 S2 can be obtained. The maximum stress simulation result is relatively small, while the displacement value is slightly larger. The joint strength of S2 significantly greater than S1. The simulation results are in reasonable range when in which is consistent with the test result for the failure mode of SSJ. The adhesive layer is reflected as a transit fracture failure is shown in figure. While the failure mode of the composite adherent is different with a different stacking sequence, the biggest influence factor of the failure mode is the fiber angle contacted with adhesive layer. When the ultimate strength is achieved, both S1 joint and S2 joint are reflected as a matrix tensile failure, and the failure level of S1 is significantly greater than S2. It is because the fiber angle between S2 joint, the adhesive layer, is zero, which can maximum bear the tensile load as fracture factors get into minimum. The failure factor of matrix tensile failure can be reflected with a range from 0 to 1, where 1 is completely failure and 0 is non-failure. The both A and B diagram represents the failure of matrix when S1 adherin was fractured, and B diagram represents failure of matrix when S1 adherin was fractured. It is the equation for the composite adherin of S1 joint is damaged, which agrees with the experimental result. Through the figure, the equation was described for the mechanical model under the tensile load, as shown in the figure, where A11 and D11 are the elements in the stiffness matrix of the unit width laminates constitutive equation. E is the adhesive end modulus and G is the shear model. Adhesive shear modulus is the adhesive thickness, and T is the thickness of adherent. The general solution for adhesive stresses are given below. Tau is equal to c suffix os plus c suffix 1s cos into x root over minus 1 plus c 2s sin hx into x root over minus a1. Sigma is equal to cos 3s cos hx into 4 root b3 by 4 cos x 4 root b1 by 4, where the corresponding boundaries conditions and determined 7 constant is I 1/4 0 minus 6 in the above mentioned expression, are the represented in the appendix in the paper by Li 13, and the midpoint of the bounded overlap edges adhesive stresses which reach their peak level as follows. Tau max is equal to tau alpha by x is equal to minus c. Sigma a is equal to sigma a by x is equal to minus c. And these are the curves for adhesive peel stress and adhesive shear stresses. At overlapping position, the adhesive peel stress rises between 115, and in B diagram overlap position raises the adhesive shear stress both up and down. So the curve position is at adhesive shear stress, the curve position is 90, and bottom it's minus 90. This is the overlap position of a adhesive shear stress. Effect of adhesive thickness. The diagram represent the adhesive thickness. Uh, the thickness of adhesive layer is also an important factor influence the joint strength composite. The study of adhesive thickness, the stacking data of S1 joint is adapted. The adhesive thickness is said to be 0.07, 0.17, 0.47, 0.77 and 1.07 mm, and among which 0.17 mm is the original joint, illustrates the connection strength of the joint with different adhesive thickness. It can be seen as the adhesive thickness increases, the connection strength increases first and then decreases. When the thickness is 0.17 mm, the joint strength shows the maximum value. From the perspective of FEA, when the adhesive layer is thin, the stress concentration at the edges large, which causes the crack of adhesive element. When the adhesive thickness is relatively thicker, the relative separation of adhesive element increases under shear force. Effect of overlap length. The overlap length of upper adherent plate is also an important factor affecting the connection strength and the failure mode. Similarly, the data of S1 are adapted. The overlap of the upper adjoint is said to be B95, 101.66, 105 and 110 mm. As the overlap increases, the connection strength also increase. Therefore, the increasing the overlap length can increase the strength of connection. The table about failure elements number overlap length is 95 mm and upper adjoint failure element is 1231. 101.6 mm is the overlap length and upper adjoint failure is 1354. 105 mm is over length and adjoint failure is 1448. This both diagram A and B is represents the adhesive stress with different overlap length. With increase of overlap length, the peak stress decrease. And A diagram represents adhesive peel stress and B diagram represents adhesive shear stress. Uh, this failure could at fracture moment of upper adjoint. Thank you.